So I guess this is a progress report. The speakers today and yesterday already mentioned that the climate model need a lot of detail, more detailed microphysics, physical representations, and cloud and aerosol are one of the most highest uncertainties in the climate model. So these projects aim to improve the parameterizations of cloud and aerosol and their coupling. And we have many collaborators because it's a very complicated task, but I will not mention all of them. This is our modeling approach. We've focused on first the regional model to test all the parameterization schemes, including cloud microphysics and aerosol microphysics and their interactions. Then we will implement these regional model tested parameterizations and put them into the global model. For regional model, we'll use the Wolfram, and for global model, we will use CSM. So next, I will show you some of the details of the parameterization and some examples. First, in the cloud microphysics, we put them. We have a long collaboration with Professor Wang. To develop the parameterizations. Then now we put it into MM5 and WRF. Let me show you the current microphysical scheme, the schematics of current scheme in WRF. The most simple one is the so-called Kessler scheme. Besides water vapor, they consider only two types of hydrometeors, that's cloud drop and raindrop, and they only consider the mass, cloud drop and raindrop. Okay, and it's gradually improved to include cloud ice and snow. Okay, and but in WSM3, it's only divided by temperature. Above the height of 0 degrees C, there's only ice and snow. Below it, there's only cloud and rain. But later, it's improved that liquid water can exist above the 0 degrees C height. And I think this is one of the most popularly used, the lens scheme of the WSM6. It also includes the grapple, okay, extra hydrometeors. But all of them are one moment, consider only the mass of the particles. But as we know, the number concentration is very important, especially for like the radiation calculation or calculating the rain formation efficiency. You need to know the information on size, and size you can get it from numbers. So the more updated version of the parameterization or included the numbers here. However, in the Thomson scheme, they only include number in the cloud ice and rain. And WDMC, there are more numbers in the cloud drops and rain. Okay, and the Morrison scheme, I think most of them have numbers here. Okay, so this is the most complete two-moment scheme, except that they didn't consider another important category of hydrometeor, that is the hail. That's very important for severe weather. So the most complicated, the Milbrand and Yao scheme, considered 13 variables to describe the hydrometeors and the water vapor. Okay, and this is our scheme. The first version, we considered the 10 variables plus aerosols. So most of the hydrometeors are two moments, but we did not consider hail in this version. However, we also consider in very detail the interaction of condensation nuclei with cloud drop and ice nuclei with cloud ice, which I will give more detail later. And the latest version, we also add in hail, and also the cloud ice are treated in more details by including the shape effect of the ice crystals. So this is another schematics of our scheme, okay, showing more of the convergence between the different hydrometeors. And I'll first show you the earlier efforts that we reformulated the parameterization for liquid type of hydrometeors. In the past, the hydrometeors are described by assuming certain kind of size distribution. then solve the size distribution integral to get the conversion rates. Okay, but the assumption of size distribution, I think, is the biggest uncertainty in this type of parameterization. They usually assume a multi-Palmer type parameterization, but I'll show you later that produce a lot of errors. So first, we improve the liquid part and also improve the interaction between cloud drop and raindrops with the small and large aerosols. So our initial effort is originally from the BIM model. It's treated the aerosol cloud interaction in very details. So this is our BIM model. This is the water component, and this is another component that is the solute content, which we also use to describe the particles. So these are the non-activated interstitial aerosols. These are cloud drops, and these are raindrops. Okay, but this detailed BIM model is very time-consuming. We cannot put it in the original model to this date. So we try to use the results from the detailed model in running in parcel mode and statistically analyze the results to generate the parameterizations. So we decompose this two-dimensional spectrum into one dimension. Then we put those larger particles, like greater than 15 micron, and counted them all as rain, and these are raindrops, and group their conversion rates. And so we have the conversion rates and also the number and size and mass of the cloud drops and raindrops. Then analyze them statistically to generate the parameterization. So we do not assume any fixed size distribution. The size distribution is solved by the detailed BIM model. Okay. So that's our approach. Convert the BIM model into the bulk representation. Okay. And also we treat the activation of aerosol into cloud drops in very detail. So these are the aerosol size distribution. Okay. Right now in this version is specified, but in our next version, in the Wolfram, it will couple with the aerosol, model aerosol distribution in the model. And these are the traditional color curve for a certain size of particle. So for a certain mass of particle. So for that particle, it has a critical radius and critical saturation ratio. And we use that information to determine which part of the size spectrum will be activated. Like if the ambient supersaturation is at this value, then all the particles larger than this cutoff size. Okay, this cutoff size corresponding to this saturation ratio will be activated. Okay, and we also, there's another special treatment of our skin is that for aerosols larger than 10 micron, we activate them directly into rain because they are already too large. It's not reasonable to put them in the cloud drop category. And this actually has a great effect on the rain initiation. In the past skins, you need to create a process called auto-conversion. I think many of you heard of that process today. But that's not the only process that can create rain. Okay. The giant rain embryo can also produce rain efficiently. Okay. Now I'll show you two examples of the application of the warm cloud part. First is a very simple cloud. It's fog. Sea fog. This from the satellite, you can see there's a patch of sea fog is moving around the Taiwan Strait. Okay, and from the this fog is in a probably dirty environment. If you can see from the AOD, okay, this is the cloud patch, and around it the AOD is actually pretty high, 0.4, 0.5. Okay, and if we look at the cloud optical depth, this is the cloud optical depth for this fog is around 7. And the effective radius also from MODIS is around 7 micron. Okay. Now we want to see if our model can simulate the fog in reasonable agreement. So we run the model with 4 existing skins. This is the Milburn and Yao skin. This is WDM6. These two are our skin, but our skin is sensitive to aerosols. So we specify two types of aerosols. One is the urban type, and this is marine type. And these top panels are cloud optical depths. And if you remember from the previous figure, it's 7. Okay, effective radius is also 7 for that fog. And this is a simulated cloud optical depth. Actually, we don't see the fog in Melbourne and Yao skin. And the WDN6 and CR, our skin, produce pretty good fog, but the WDN6 optical depth is too low. Okay, our skin, the urban type is close to 5 or 6, highest is around 7. Okay, so this is closer to observation. If you use the maritime type of aerosol, the optical depth is also very low. Okay, so since our skin can capture the influence of pollution on the fog formation. And these are the size. You can see WDNs produce too large size, actually over 50 micron. That's way too large. That's not reasonable. Okay, and our skin, the urban type, produce about, let me see, here's around 5, and some patches is between 5 and 10. Okay, so I think these sizes are a bit more reasonable. A second application is to see the influence of aerosol on very strong system, typhoon. This is a very strong, very special typhoon called Neri. It formed in this area and going south. It stayed in the East China Sea for over 1 week. So we think it should have a very strong influence on the pollutions in the Eastern China, Taiwan, and even Japan. Okay, and these are the simulations using the Wolfram version. We see that the structure of the typhoon varies with aerosols. This is natural aerosol, and this is including the anthropogenic aerosol. You can see the difference in structure. And also, not only the structure, but also the strength and even the direction of movement can be affected by the aerosol in some cases. But I won't show you the detail today. If you are interested, we can talk about it maybe tomorrow in the breakout session. Okay. And this is the same case. And well, I want to show you one figure that's seldom discussed. That is the size of the particle. Are the size reasonable or not? Because we want to include the second moment number to produce good size. Okay, but many microphysical skin cannot produce reasonable size, just like I showed you before for the fog case. Now for the typhoon case, these are the simulated evolution of the size over northern Taiwan, and which we have a corresponding disdrometer measurements. And the disdrometer measurement shows the mean size is around, the diameter is around 1 to 2.2 millimeter. Okay, and the WDMCs can produce only 0.3 in radius. So it's too small, way too small in this case, too small range. And the marine case produced too small particle in the beginning, but then it's in the right range. The range of the 1 to 2.2 is indicating the dashed lines here. Okay. Now for the urban case, it always stay in these two limits. So our size is so performed pretty good. Okay. Our next effort is to improve the interaction between the ice nuclei and the clouds. So I talk about the ice nuclei and how it nucleates into cloud ice. We try to unify the representation of ice nucleations. So the same formulas can be used for every kind of ice nuclei. So this is the classical nucleation rate theory, the formula. And in this formula, there are only two variables depends on the ice nuclei. That one is the contact angle, the other is activation energy. So we analyze many of the laboratory work, the data like the points here, okay, the dots here, to derive the contact angle and the activation energy, so that the same equation can be used for different type of ice nuclei. Okay, and the solid curve here indicates our formulation. So you can see it fits very well most of the laboratory experiment. except maybe the Pseudomonas syringae, this one of the bacteria here. So we will apply that in our model, just using this table. And the first effort is trying to study the effect of dust, since dust is the most important ice nuclei in the atmosphere. But it also has a lot of effects, not only through the ice process, but also through the liquid phase processes. So one of the efforts is to study in very detail how dust affects clouds. In the past, we only consider ice nucleation. Okay? And there are many ice nucleation, like immersion freezing, deposition nucleation, and so on, and also the contact freezing. And in this model, we also consider the collection of cloud drop with dust, and of course, the dust collected in the cloud drop can activate the cloud drop into ice if the temperature becomes cold enough. That's the so-called immersion freezing. We also consider the activation of dust into cloud drops. Okay, this is very rarely treated in most models, because dust, large dust particles can be active, pure dust can be active in cloud drop. And also if they are coated with pollutants, solutes, they can be very good condensation nuclei. So also consider this activation effect and their forming of cloud drops and nucleations. We also consider recycling. So the dust collected into cloud drop and raindrop will be released back into the atmosphere when they evaporate. Okay. Of course, if they are not evaporated, they'll bring down as precipitation to the surface. This is one case showing a dust storm following the cold front in the East Asia. And I won't show you the detail, but only show you the difference. The blue line is the simulation without dust effects, okay? And the red line, the simulation with the dust effects. And this is the precipitation. You can see a significant difference here. And also, since it doesn't modify the cloud, you see also large difference in the short wave radiation and the long wave radiation. And this is the profile of the micropieces. These are differences. So it created a lot of cloud ice snow. Red means increase, okay, and grapple. Rain at the top decreased because the water vapor is also cloud drop are depleted by the extra ice crystals. But at the below 0 degrees C level, because of a lot of snow gravel form, they also melt into form raindrops. So net effect is to increase the rain. That's why in the previous diagram we see the increase of precipitation. A second effort of the ice nuclei is the phytoplankton over the oceans. Okay, we simulated the production of phytoplankton in a case of typhoon. Here you see case of hurricane or typhoon in this area. The strong wind will carry up the phytoplankton into the atmosphere. So you see the concentration of phytoplanktons in these three diagrams. This is concentration in the interstitial phytoplankton, and these are when they already get into the cloud drops. You can see the phytoplankton can be bring up to the very high levels to form the ice particles. And these are the effects of the phytoplankton. You see large change in cloud ice, snow, and gravel and rain. Actually, they enhance significantly the surface precipitation. Okay. Now these are the ice nuclei effects, but we still think the ice phase representation in the current schemes are quite crude. So right now we are improving the ice microphysics representation. Remember, here we only, in the earliest effort, we only modify the liquid phase parameterization, but the ice physics are still the resonance old scheme. Now we are modifying all of them. The first thing we worry about is the representation of the size distribution. Here's one example. For raindrops, snow, or gravel, this is traditional way to do it. It's assuming the number dependence with the size is log linear. That's so-called Marshall-Palmer. Okay. So if you imagine these particles are growing by vapor deposition, then after a while, what will the size change? What will the size distribution change? The traditional way is if the one moment it fixes this point, so the particle grows, but only the larger particle grows. The smaller one doesn't grow. Okay. If it's two moments, maybe the slope changes. However, you still maintain a lot of very small particles. Okay. In effect, those small particles grow to a larger size, so there should be a gap in the smaller particles. But the current treatment forces you to have a lot of small particles. Okay. So I think the gamma distribution is more appropriate. The smaller size will decrease with time. Actually, the size can get narrower by condensation. So this is the gamma type of distribution. Okay. Another modification is the shape of ice crystal. The current scheme all assume the ice crystal are spheres, but you know if you see the hexagonal crystal, you know that's not true. Okay, and the shape has a lot of effect on the growth, the collections, the force speed, the radiations of the ground microphysics. So we included shape effect according to the beam model I created many years ago. We have a formulation to describe the change of shape. The 5 here is the aspect ratio, the c-axis divided by long axis, the aspect ratio. So you formulate the shape as in terms of the aspect ratio. And the change of the aspect ratio is dependent on the change of volume, that is the deposition growth, but modified by the coefficient as a function of temperature. I won't get into the detail of that. This is for beam model or single particles, and we incorporate that into the bulk model, the model model. So the factor here, actually, we define the shape moment as the 5 times d to the third power. And we solve the equation for that and also the conversion rates. Okay? And that has been put in the model. Here are some examples of the effects. The blue line here is the traditional way. Sphere, a spherical particle with 2 moments. And this is growth, this is time, and this is the mass. Okay? And the top curve is the calculation from beam model. That's the most accurate one. So you see a very large difference, maybe more than 2 times difference in terms of the mass, so the mass growth. But if we put in, this is 3 moments, but it's still sphere, it improved a little bit. Only it's still less than half of the supposed mass. But if we put the shape, this 2-moment shape, this 3-moment shape, you can see very large improvement in the growth of ice crystals. Okay? And I will skip the other 2 diagrams. And this shows you the actual evolution of the shape. The bracket is original shape, and these are the evolution from the beam model. It's actual beam model calculation. You see the spectrum grow, but also become narrow, very narrow later. And the 2-moment scheme still keep the very small particles, so that's not good. Okay, but in the 3-moment scheme and with the shape modification, it gets much closer to the beam model results. Okay, and now we put that the parameterization scheme into both the gamma distribution and the shape parameterization into the work to simulate one of the diamet cases occurred in England. This is we simulated this front system. Okay, I'll skip this. And this diagram shows you the difference between the spherical simulation and the one with shapes. Okay. The blue curve is the spherical 2-moment scheme. You see a very large difference in the pristine ice. Let's focus on the red curve. That's the shape and 3-moment scheme. See very large difference in ice, aggregates, and hail. Okay, but not so much in the range of cloud drops. And this is in terms of number. It not only affects the mass, but also the number. Also the cloud ice, gravel, snow number are all affected. And also hail especially. And this is size also show a lot of difference. Now, the faster growth by including shape, will also affect the latent heat release in the cloud, of course, the strength of the convection. Sorry. This one is the number concentration. You can see our simulation is pretty good. The maximum concentration is 80 per liter, and this is from aircraft observation. It's also close to 80. Okay. And without this, as you see in the previous diagram, the number will be too low. Okay. And this is the shape. Okay. Aircraft also have the crystal image to provide the information on shape. However, because it's 2D image, they can only identify the column when the C-axis ratio is greater than A. But if it's spherical, we cannot see the other dimension. So I can only show you the aspect ratio of columns, not the plates. Okay. And this is the observed column aspect ratio. It's mostly between 1 and 10. And the average is around almost 2. Okay. And this is our simulation, but this one is in log scale, between 1 and 10. Mostly, although we have some of the crystals maybe too large, but I think some of the very large crystals cannot be detected by this 2D image anyway. Okay, and another thing that's worthwhile to noting is that usually we know the column is usually formed between -5 and 10, not between -10 and 20. But from observation, we still see a lot of columns. Okay, that's it. Because of the shape memory effect. And if you look at the older models, when they assume the isotope has shape, they are always fixed. Okay, you cannot find color in this temperature range. But in our model, we do see that because our model also considers the memory of the ice crystal. So when its original column, but you fall into the shape regime, it still maintains its original shape, but change gradually toward the place regime. Okay. So our model seems to be able to capture these kind of effects. This is the heating rate. Okay, this observed heating, I think, is converted heating rate. Maximum is 6 degree K per hour. And without the shape effect, you get only about maximum about 3. But with the shape effect, we get pretty much the same order as the observation. Okay. So these are our efforts in the modification of the cloud microphysics. And the latest version by Dr. Chen also included the hail part. So now our scheme is very complete. And the total variable tracked are 24. And second part of our efforts is the improvement of aerosol microphysics. And we put that first in the CMAC model, tested, then implemented into Wolfgang regional model. And for the aerosols, we also assume it's modal type of distribution, but we use 3 moments, okay, for each mode. And so we have maybe 2 or 3 modes for sulfate, 2 or 3 modes for mineral dust, and also we consider the mixture when they interact. Okay, and this is not included in any current model. The only way to form mixture in current model is the condensation of sulfuric acid onto dust. But we think that that process is either false or too weak. And we think the main process is the collision. So we included the coagulation between dust and the sulfate particles to form a different type of mixture. Of course, this can be applied to sulfate and soot also. And to parameterize this, we adopted a similar approach as earlier. We used a statistical approach to run the model in very detailed, the BIM model, then analyze the results to fit the statistically to get the conversion rates. Here is an example of our scheme. Our scheme is the red dots, and the cross is the current scheme in, I think, in Wolf and also in CMAC. That's a Minkowski scheme. Okay, you can see our results are mostly lying in the diagonal line here, but theirs has a bias. Okay, and this shows the errors. Our errors is much smaller, but our computational time is the same as theirs, the same as the Minkowski's. Okay. And here's one application. We simulate a dust storm formed in northern China, and the dusty air moved toward the Pacific. They will pass through the polluted region here. So try to simulate this effect. And here is the dust area, and this is the, we call it hygroscopic particle, mainly sulfate and nitrate. And soot, we have not considered the mixture of soot yet, so this is pure soot. And this is the mixture. You see, when the dust is transported downwind, this is after the front passage. Like most of the dust is converted into mixtures. Okay. And with the mixture effect, we can see this is a measurement in Taipei showing the single scattering albedo. The black line here is measurements, and this line is calculated assuming there's a mixture effect. And the top curve is without the mixture effect. You can see with the mixture effect, the result is much closer to observation. And this one shows the difference between the aerosol mass, area, surface area, and number concentration. This with and without the mixture. You can see very large difference. But the difference is to decrease the mass in the upstream, but increase in the downwind region for mass and surface area. Okay? And also a little bit on the number. But number is more complicated because it also involves the nucleation and other processes. The lowest diagram is the considering the mixture only by condensation of sulfuric acid on dust. Okay, and without it, you see very small change. So we think the condensation of sulfuric acid onto dust is less important than coagulation. How much time I have? 3 minutes? 8 minutes. Okay, good. And so with that, we can estimate the number of mixture dust acting as condensation nuclei. Okay, so this is total condensation nuclei with mixture and also the hygroscopic particles. And this is if we neglect the mixture effect, you can see very large difference in the condensation nuclei. Okay, the unit here is 4, 5, and here is 2. Okay, you can increase the number of condensation nuclei by 2 or 3 times more. Okay, because of the coating on the dust. And this is the estimation of the isonuclear effect. Okay, when the dust is coated with the solute, its ability to nucleate into ice by deposition nucleation is inhibited. But its ability to form ice by immersion freezing is increased. Because with coating, you can absorb water, then the water can freeze by immersion freezing. So at lower temperatures, the mixture effect will decrease the ice nucleation capability. This is without the coagulation missing minus with. So you see it's decreased. But at this one is if the air temperature is higher, I think this is around 10, minus 10, you see increase in ice nucleation. That's very interesting. The effect can be opposite at different temperature regimes. Okay, and the last part of the progress is the implementation of the above mentioned microphysics and aerosols into global models. Now we put it into the CSM model. And the first effort already shown in the poster yesterday, that is the modification of the cumulus parameterization to include the aerosol effect. The past cumulus parameterization do not consider number or aerosols. Now we included our two-moment scheme, very simple scheme, into the Zhang and McFarlane cumulus parameterization. And this is observed cloud-leak water path, okay, to observation. I don't know which one is more correct. Okay? But this is the control run without the original CAN 5. And this is the one including our parameterization. You can see the liquid water path is much improved in the tropics. And also the ice is improved. This is a cloud set representing the observation. This is without, this is original skin. This is our modified skin. You can see the ice, especially in the tropics, improved quite a lot. Okay. We also incorporated the aerosol skin into the CSM. Okay. But for comparison purpose, the current CSM model is a model size distribution, but with only 2 moments. So in order to compare with them, we also reduce our skin into 2 moments for comparisons. And this is simulated the aerosol number concentration. And this is the difference between our skin and the original MMM3 in CSM. Actually, there's a large difference in the number concentrations. In the polluted area, the difference is small, relatively small, about 10%. But in the remote region, like in the Arctic, the difference can be several hundred times. Okay, very large in the remote, clean areas. And this is the mass. The mass difference is a bit smaller. And this is scatter plot comparing with the observed SO2, organic carbon, and black carbon. Okay. The black dot are the original CHEM results, and the red dot are our results. They're supposed to be similar, otherwise our skin will have some problems. Okay. So you see some differences, but that's mainly because we fixed 1 moment. And right now we are trying to see if we include a 3rd moment and how much difference we make. Okay. So that's our progress. You can see from the color bar here, the regional model, I think we are almost finished for the cloud and aerosol. But their coupling, I think, still needs some work. And the global model, we're just in the starting stage. And hopefully we can finish in the next 1.5 years. So our current issues are, first, the activation of CCN skin in the global model needs special treatment because the cloud is a subgrid scale process. So our skin is very sensitive to aerosol size distribution and also the updraft speed. So, but in the global model, what is the updraft speed of cloud? We have to take special consideration of that. So we try to use the spectrum of updrafts, either derived by the kinetic energy or some other parameterization or diagnosis. And the second one is, right now the ice nucleation is very important, but where is the ice particle generated? Especially the natural one, the ice the dust, volcanic ash, bacteria, and even the phytoplanktons I showed before. How do you simulate it? I think that's a big question. Okay. And also, of course, anthropogenic ice nuclei like soot, fly ash. I don't think they are very properly simulated. And this is a very complicated test. The aerosol recycling and scavenging. This is also the worst treated processes in current skins. For example, I don't think what the most updated version do in some way consider the recycling of aerosols if the cloud evaporates. But I'm not sure how accurate are they treated. Okay. But in our skin, we track all the, including solutes, including the dust, inside the cloud drop, raindrop, snow, graupel. So when they evaporate, we can return them to the atmosphere, so do the recycling. Okay. And also, these aerosols can be transferred when the cloud ice convert into snow or graupel. Okay. But we need to do a lot of tracking, and also the advection takes a lot of computation time. Okay. So we haven't figured out yet how many species, aerosol species we need to include in the model. And also the treating all those particles and also particle in particles need accurate advection scheme. Okay, so we are thinking how to improve the advection scheme. And also there are some issues of below cloud scavenging. For instance, if it's a convective cloud, the most amount of aerosols that can be washed out is below that cloudy area. But current treatment is is washing out all the aerosols in that grid. I think that is not a proper way to do the scavenging. So how we treat the below cloud and also in-cloud scavenging require extra attention. And the last effort is some of the microphysical schemes in the global model is actually controlled by the macro physics, like how much water vapor can be condensed is controlled by the so-called macro physics. Then the microphysics scheme cannot determine the amount of condensate. And I think that's a major flaw of the current scheme. We're thinking how to make the macrophysics and microphysics to be very consistent and compatible. Okay? And hopefully some of you can join us for these very difficult efforts. And that's all my talk. Thank you.
Thanks, JP. Okay, Frank.
This is a very impressive talk. May I ask, this your scheme is going to be implemented or is implemented as an official version in the NCAR CSM1 model? That is first question. Second question, what is the impact for this implementation in the NCAR model in radiation budget? And then last one, why hair is important to be considered recently? The hair, you know.
Hair.
Hair, yeah.
Yes. Okay.
So, thank you.
3 questions. I'll answer it quickly. First, we want to put it into the official options, but we need to do some tests before we have most confidence on it. And the second question is, it has a lot of influence on the radiations. Like the older global model, they just diagnose the effective radius. But I think most of the effective radius is derived from observation. But most of the observation is done probably near the cloud base or inside the cloud. Okay. But the effective radius changes with the depth of the cloud. And the satellite or the sun sees the top of the cloud, not the bottom of the cloud. So I think there's a mismatch of the effective radius. So we actually need to resolve the effective radius as a function of height. And this kind of detailed scheme can help that. Okay. And what is your third question?
Never mind. Yeah.
Never mind. I'll talk to you later, maybe tomorrow. Computation cost.
That was one of them.
Oh, okay. That's a very difficult. Oh, hail. We haven't tested hail in global model. I don't think we need that in global model yet. But in regional model, it's very important for deep convection. Yes.
My opinion, rather your other input and not a word on that for all these.
Yeah. Yeah. Because the advection time is proportional to the number of species or moments. Yeah. Yeah.
Well, yeah, I mean, and then you're including so much extra physics, good physics, that it gets more complicated as well. I mean,
We'll destroy other physics. Yes.
Quite restrictive also in order to resolve some of the process.
Yes. Yeah.
So it would be very interesting to chat offline because we could talk for hours and hours
Yes.
about the compromises that went into the first incarnation and what we were doing differently.
Yes,
And
certainly.
there are advances that are taking place, yeah, beyond what you know, or what you've been able to talk about in this talk also.
Yeah. We have time to talk about it tonight.
Okay, so no other question there. Thanks, JP, again.